that is it should be reflexive, symmetric, transitive, and should satisfy the substitution law. These things should be true when you are saying that you have defined something which says two objects of the same nature are equal. For that criterion of equality to be a legitimate one, it should be an equivalence relation, that is, it should be reflexive, symmetric, and transitive, and it should also satisfy the substitution law. The substitution law, however, is something that not only depends on the definition of your equality, but it also depends on the operations and functions that you may define in that system of objects. For example, if you define a binary operation and you have you have defined a class of objects where you have two objects A and B, and you define a binary operation star, so A star B will be again some such object in that class. Now if it happens that the class has two objects A and A prime, and according to your definition of equality, A is equal to A prime, not literally but according to your definition, then it better be the case that if you replace A by A prime, then this product is unaffected. That is, whatever you end up getting, they should be the same. That is the law of substitution. If you substitute an equal quantity, then the operation or any functional value should not be affected. If you, for example, define a function also on this class, then f of A should be equal to f of A prime. Okay, but since on the system of integers we so far have no operation or anything like that defined for us, so we will verify the substitution law afterwards. When the operations are defined, then only we will verify the substitution law. However, now we can verify reflexivity, symmetry, and transitivity. Among these three, we will leave reflexivity and symmetry in the first exercise, and we will verify only transitivity. So we leave reflexivity and symmetry to exercise 4.1.1. We only verify transitivity here. Okay. So let A, B, C, D, E, F be natural numbers such that the integer A dash B is equal to the integer C dash D, and the integer C dash D is equal to the integer E dash F, and these equalities are the ones we have defined there in that our actual definition. Then what do we have from this equality? A plus B should be equal to C plus B, and from this one we have C plus F is equal to E plus D. Okay, so these are equations in the system of natural numbers. They are true because we have equality there between these integers. Now what can we conclude from these two equations? Adding these two equations, we get A plus B plus C plus F is equal to C plus B plus E plus F. Now this is again an equation in the system of natural numbers, and recall that in the system of natural numbers we have cancellation law, so that can now be used, and that is coming from proposition 226 by we have, so the common terms on both sides are C and F. So if you cancel them, you will be left with A plus D okay, am I writing it correctly? C plus F is equal to E plus D. So A plus D plus C plus F is equal to C plus B plus E plus D, sorry. Yeah, it felt like something was wrong. So the common terms are C and D. So we have to cancel them. So A plus F becomes equal to B plus E. This implies A dash B is equal to E dash F. A plus F equal to E plus B or B plus E. So that's it. This shows, or thus the equality of two integers is transitive. Let us also mention that at this stage we will not be able to verify the substitution law. We will verify the substitution law only after defining the algebraic operations on the algebraic operations of addition and multiplication on the integers and also an order relation on the integers. We will eventually also say when one integer is greater than another integer, so those things will also come. When we do them, when we define them, then and there we will also verify the substitution law. For advanced operations like exponentiation, there is no need to verify the substitution law. No need to verify the substitution law because they will be defined in terms of more basic operations for which the substitution law will already be true. I mean, when we get to more advanced operations, since they will be defined in terms of the basic ones for which we will have the substitution law verified, so automatically the law will be true for the advanced operations. Okay. So now we have come to the stage where we can define the first two basic operations of addition and multiplication. So this is definition 4.1.2. The sum of the two integers a dash b and c dash d is defined as this: a dash b plus c dash d is defined to be equal to a plus c dash b plus d. The product of the two integers a dash b and c dash d is defined as this. AC plus BD dash AD plus BC. Hope this is visible. AC plus BD dash AD plus BC. It is normally what you will get if you just simply multiply these expressions out as if this is just A minus B and C minus D. You see, you will get AC minus AD. So you have here AC minus AD, and then minus B times C is minus BC, and minus B times minus D is plus BD. So that's the thing. Okay. Okay, I need more ink. Thus, for instance, 1-4 plus 5-1 say is equal to 6-5. We can just simply see, for addition we are just adding the, like it's like adding two ordered pairs. If you know such an operation, you have to add the first coordinates and you have to add the second coordinates. A is added with C and B are added up. So 1 plus 5 is 6 and 4 plus 1 is 5. There is, however, one issue that needs to be addressed. Note that (1-4) is equal to 2-5. So if we replace 1-4 in 1-4 plus 5-1 with 2-5, the result ought to be the same. That is, we should get this 1-4 plus 5-1 is equal to 2 dash 5 plus 5 dash 1. It should be the case, otherwise the operation addition that we have defined is not well defined, and this is what we mean by the verifying the substitution law, because we are substituting in place of 1 dash 4 we are substituting 2 dash 5, which is equal to this, but the binary operation should give the same result. If that does not happen, then this operation not only depends on the integer but also what representation of the integer we are using. That should not happen. If that happens, then our definition is not well defined and that cannot be used. It will be of no use. Now in this particular case, you can of course see that it's the thing that 1 plus 5 is 6 and 4 plus 1 is 5. So this is 6 dash 5. Here however we would get 7 dash 6, and you can see that 6 dash 5 is equal to 7 dash 6. Why? Because 6 plus 6 plus 6 is equal to 7 plus 5. That's why these two are equal and we actually have equality. But this is only one instance. What about in general? Do we really have this thing in general? And to answer that question, we have a result, and that result is this one. This is lemma 413 and it's named accordingly. Addition and multiplication are well defined. And the specific statement goes like this: let A, B, A prime, B prime, C, D, B natural numbers if A dash B is equal to A prime dash B prime, then it does not affect sum. A dash B plus C dash D is equal to A prime dash B prime plus C dash D, and A dash B times C dash D is equal to A prime dash B prime times C dash D. And also C dash D plus A dash B will be equal to C dash D plus A prime dash B prime, and C dash D times A dash B should be equal to C dash D times A prime dash B prime. Thus, addition and multiplication are well-defined operations. That is, in simple language, equal inputs give equal outputs. You may wonder that proving this one and this one is enough. From them, these two things will follow. But keep in mind, we haven't said anything about commutativity, whether this addition and multiplication we have defined are commutative or not, that we still don't know. They will turn out to be commutative, but we still have to prove that. So before we have that commutativity, these two statements have to be separately proved. This one does not imply this one, or for example, this one does not imply this one. The proof is not very difficult, but you have to carefully do it. Okay, so first of all, we need to prove this one. Let us first prove a dash b plus c dash d equal to a prime dash b prime plus c dash d. The left and right hand sides evaluate to a plus c dash b plus d and a prime plus c dash b prime plus d respectively. So this is the left hand side and this is the right hand side according to our definition of addition. We want to show that these two things are equal. We want to so these things are equal means these two integers should be shown to be equal. So we can invoke our definition of equality here. So we want to show this a plus c plus b prime plus d should be equal to this plus this should be equal to this plus this. A prime plus c plus b plus d. This is something we want to prove. Okay. Now what is given to us? The only thing given to us is this equality from a dash b equal to a prime dash b prime. We have a plus b prime equal to a prime plus b, and this is an equation in the system of natural numbers. we want this and we want this. So the extra terms we need are C and D. So we add C and D on both sides. Adding C plus D on both sides we get, and we can write the terms in a rearranged manner. Instead of writing A plus B prime, we write A plus C plus B prime plus D, and we are allowed to do so because in the system of natural numbers we have all the properties available to us. Addition is commutative, associative, all those things are already there. And on this side we can write A prime plus C plus B plus D. So that's it, that's what we wanted to prove. So from here we can do back calculation and we will end up here. This proves okay. So next, multiplication. Next, we prove A dash B times C dash D is equal to, okay, let me write it there, no need to clutter the space unnecessarily. This should be equal to A prime dash B prime times C dash D. Same strategy, the left hand right hand sides evaluate to, okay, now here it will be slightly bigger, AC plus BD dash AD plus BC and dash okay. We want to show that these two integers are equal. That means this plus this, AC plus BD plus A prime D plus B prime C should be shown to be equal to A prime C plus B prime D plus AD plus BC. Or if you take C common out from the first and the fourth term on the left hand side, then you will get C times A plus B prime plus, if you take common out D from the middle terms, then you will get A prime plus B. A similar job done on the right hand side will give us what? If we take C common out, we get A prime plus B, and if we take D common out from this one and this one, we get A plus b prime. Note that in writing these expressions we have used whatever order we like for the multiplications and also for the addition. That is because these are ordinary operations in the system of natural numbers. So where we know that the operations are commutative, and we also have the distributive law that allows us to write the things like this, that allows us to take common terms outside and write it as a product like this. Okay, now since this we have a plus b prime is equal to a prime plus b. So that's it. You multiply this by once by c, once by d, and you can see from this equality itself that these two things are equal. Thus, multiplying both of them by c, we get c times a plus b prime plus multiplying both sides by d but in the opposite order. We take this one, d times a prime plus b. So in place of this we can write this. And in place of this we can write this plus d times